Now P block elements, a new chapter. In periodic table, the P block is on extreme right side, and there are 6 groups. Group number 13, 14, 15, 16, 17 and 18. So there are total 6 groups in P block. 13th group begins with boron, so it is called boron group, or it is also known as third A group. 14th group is 4th A group. 15th group is 5th A. 16th group 6th A. 17th group 17th A. And this is 8th A or 0. So 13th group is having valency 3. 14th group is having valency 4. 15th group is having valency 5. 16th group 6. 17th group 7 and 18th group 0. Boron, silicon, germanium, arsenic, antimony, tellurium and iodine are semi-metals. Left side of the semi-metals like aluminum, gallium, Pb, bismuth, etc. are metals, and on the right hand side you will find non-metals. So all types of elements are present in P block. In period, if you go from left to right, atomic number increases, atomic radius decreases, ionization enthalpy increases, electronegativity increases, oxidizing power increases, metallic property decreases. In group, from top to bottom, atomic number increases, atomic radius increases, ionization enthalpy decreases, electronegativity decreases, oxidizing power decreases, metallic property increases. Now we'll start group 13. It is also known as boron group. Boron, electronic configuration helium 2s2 2p1, aluminium, neon 3s2 3p1, gallium 31, argon 3d10 4s2 4p1, indium, krypton 4d10 5s2 5p1, thallium 81, xenon 4f14 5d10 6s2 6p1. Occurrence: boron is available up to 0.0001% by weight, aluminium 8.3% by weight. So this is the third most abundant element. Minerals of boron: borax Na2B4O7 10H2O, kernite Na2B4O7 4H2O, colemanite Ca2B6O11 2H2O, orthoboric acid H3BO3. Boron is available in California, Turkey, and from Puga Valley of Ladakh and Sambar Lake of Rajasthan, India. Borax, kernite, colemanite, orthoboric acid. Minerals of aluminium: bauxite Al2O3 XH2O, orthoclase KAlSi3O8, cryolite Ne3AlF6, corundum Al2O3, beryl B3Al2Si6O18, mica KAl2Si3AlO10OH twice. Bauxite, orthoclase, cryolite, corundum, beryl, mica. In India, mica is found in Madhya Pradesh, Karnataka, Orissa and Jammu. India is world largest supplier of mica. gallium from germanite, which is a complex sulfide, or from complex sulfide of zinc, copper and arsenic. Indium from sulfide ore of lead. Now physical properties. Atomic radius of aluminium is more than atomic radius of gallium. Normally, if you go from top to bottom in group, atomic radius increases. But here, atomic radius of aluminium is more than atomic radius of gallium. Why? Well, in aluminium, there are 13 protons in nucleus and 2, 8 and 3 electrons. So total 3 orbits. Outermost shell has 3 electrons and inner shell has 2 electrons in first orbit, 8 electrons in second orbit. So in aluminium you will experience screening effect of only s and p orbitals only. Therefore aluminium has more screening effect. While in case of gallium there are 8 plus 10, 18 electrons in third orbit. Out of this, d orbitals contain 10 electrons only, and these 3 electrons are in fourth orbit. Well, d orbitals are directional and they are always away from nucleus, and therefore there will be very less screening effect of d orbitals on these 3 electrons, and therefore in gallium comparatively screening effect is less than that of aluminium. And if screening effect is less, then electron of outermost shell has less attraction of nucleus, and therefore more attraction of the nucleus, and therefore gallium is having somewhat small ionic radius than aluminium. So 3d orbitals are absent in aluminium, while in gallium 3d orbitals are present. In aluminium there will be more screening effect. 3d orbitals are large in size, which decreases magnitude of screening effect in gallium. Aluminium has less nuclear charge. Gallium has more nuclear charge. So attraction of nucleus on electron is less. Attraction of nucleus on electron will be more. Therefore gallium is smaller than aluminium. Ionization enthalpy. If you take first ionization enthalpy, then first ionization enthalpy of 13th group is always less than that of second group. That means the first ionization enthalpy will be less than alkaline earth metals, and the reason is there is only one electron in p orbital, and therefore it's easy to remove electron from p than s, so that boron, aluminium, gallium, etc. having less ionization enthalpy than beryllium, magnesium, calcium, etc. Now, first ionization enthalpy of the group. Here we can see that boron is greater than aluminium, is less than gallium, greater than indium, less than thallium. In this case, we can see that the ionization enthalpy is not in order. Boron is comparatively higher ionization enthalpy than aluminium, and you can write the values also. The first ionization enthalpy of boron is about 801 kilojoule per mole. Aluminium is 577 kilojoule per mole. Gallium 579. There is very less difference between first ionization enthalpy of aluminium and gallium, but we can say that aluminium is having less ionization enthalpy than gallium. Indium is 558 kilojoule per mole, and thallium again 589 kilojoule per mole. So this is the trend in 13th group. Now why? If we compare boron and aluminium, then the size of boron is less than aluminium, and screening effect is less than aluminium. Therefore, boron has more attraction of nucleus, and so it is very difficult to remove one electron from 2p1, and therefore ionization enthalpy of boron is greater than that of aluminium. Now we compare aluminium and gallium. So here the gallium is having size less than aluminium. Screening effect is less than aluminium. Therefore, gallium has more attraction of nucleus than aluminium. Therefore, ionization enthalpy of gallium is greater than that of aluminium. But not much difference. Well, indium. Now we have to compare gallium and indium. In indium we have 4d orbitals, which reduces the magnitude of screening effect, again an increase in nuclear charge, therefore, and which is overweighing the screening effect, and therefore the ionization enthalpy of gallium is greater than indium. Thallium and indium. The presence of 4f orbital and 5d orbitals decreases the reactivity of thallium. Screening effect is overweighted by nuclear charge, and therefore thallium is having higher ionization enthalpy than indium, because in screening effect of thallium is greater than that of indium. Metallic character. Aluminium is good conductor of heat and electricity. Reduction potential of aluminium minus 1.66 volt, gallium minus 0.56 volt, indium minus 0.34 volt, thallium plus 1.26 volt. So from aluminium to thallium, electropositivity decreases, reduction power decreases, metallic character decreases, melting points and boiling points. Well, boron is 2453 Kelvin, aluminium is 933 Kelvin. Here you will find large difference in melting point of boron and aluminium, and boron is having highest melting point. Why? Well, their melting point is related to crystal structures, and boron is having covalent network solid. So many boron attach to each other and form polymer. Therefore, melting point is very high. Aluminium, indium and thallium having close pack arrangement. Like metal. These two are also having close pack arrangement. Like metal. But gallium is something different. Aluminium, indium and thallium have close pack arrangement structure like metals, so their melting points are comparatively high. But gallium is only 303 Kelvin. That means at normal temperature it might be in liquid state, and it is having very low melting point because of unusual structure, and that is molecular solid structure like Ga2. Therefore, its melting point is very low. Boiling point: boron, aluminium, gallium, indium, thallium, etc. And here there is a regular trend that boron to thallium boiling point decreases. Nature of compound. For boron, first ionization enthalpy plus second ionization enthalpy plus third ionization enthalpy is very high, and therefore boron does not form +3 state. Hence boron forms covalent compounds. From aluminium to thallium, sum of ionization enthalpy decreases and they form ionic bonds. So aluminium can form covalent as well as ionic bond. Gallium to thallium form ionic bond. Oxidation states. Boron theoretically we write +3, aluminium +3, gallium, indium, thallium along with +3 they show +1 valency also. And in gallium to thallium you will find that the tendency of s electron to participate in bond formation decreases due to intervening of d and f orbitals, and the screening effect of ns2 orbitals become poor and inert pair effect become more predominant. That means last orbit 2 electrons of s will not be given to any other elements, but they behave like inert configuration. So ns2 electrons will be merge into inner shell filled orbitals, and therefore gallium, indium and thallium have tendency to release one electron only, and so they are showing +1 valency. So from gallium to thallium the stability of +1 increases, and this is evident over here. The thallium +3 except 2 electron get reduced to thallium +1, and standard reduction potential is +1.25 volt.